Okay, I guess we can start now, I guess. Yeah. So yeah, I hope you all have filled the attendance. Yeah, I guess that's it. We just start. Okay. So yeah, welcome back. So today I'm going to discuss about quiz 2, the second session. So quiz 2, right? Based on the outline, it should be still the same. It should be like about column loads and simple frame construction. Yeah. So first things first, you should have a few files. First one is this one. It's the one that I'm going to write on. Second one is this one. It's the simple. Should be like this one. Is the cheat sheet. Yeah. So as promised, I will give you the quiz 1 and quiz 2 cheat sheet. But if you want the full version, $10. Yeah. So yeah. And then lastly is actually the section property table. It's this one. Yeah, I think it's yellow. The one that I sent is the cover is blue, but the pages are yellow. So I think for quiz 2, you are required to print this. So just a reminder. Okay, I guess I'll write it down. Okay, so one cheat sheet, $10 for full version. Okay, number 2 is don't forget to print section properties table. I don't know if no, not all, not all. I send you the pages to print. It's just the what's it called? It's the yellow pages and also the bold and the weld, if I'm wrong. Yeah, just refer to. Yeah, so it's not. Don't print all the 700 pages. It's supposed to be only this thick only. It's around 100 pages. Divided by 2, so 50 lah. 50. Yeah, legit. Yeah, don't print whole 700. Okay. Okay lah. Refer pages. Refer to group. Yeah, so these are 2 reminders. Reminders. All right, so let's just start. So as usual, I'll do the concept first before I go to the calculations. And then actually, right, this prof is, I think, is quite famous for repeating the questions. So actually, if you want, just skip to the end, but okay lah, as in it's better if you know the whole understanding, because if they change a bit, then GG. So yeah, so first I just want to have a quick review. So here's the design process. You always get the loading first, get the loading, factor the loading, do some structural analysis, then design, and then build. So I guess this one you can see yourself, because I'm not going to go through this like in detail again. Yeah, refer to my first peer tutoring or just read the slides. I think you can understand. Then second thing to review is the load part. So okay, before the load part, we have partial factors. So for ULS means anything to do with shear, bending, basically the structural failure, structural failure. Well, serviceability, this one is SLS. So this one is anything to do with deflection. Yeah, so just review lah. So I hope you remember for ULS, it's 1.35 times permanent plus 1.5 times variable. So this one I think you should know. This for ULS. And then some more review. Yeah, I'm going this very fast because I need to cover like the whole thing. So loading part again, remember it goes from the slab goes to the beam goes to the another beam if there is, and it goes to the column. Okay, then column foundation. Yeah. So there's one-way loading and two-way slab. This is just to refresh your memory. Okay, I won't go in detail. Now here's the new part, which is columns. So the second quiz will all about columns. So first things first, this is just to make you aware. There are a few types of steel sections. So there's the universal beam, universal column, channel angles, and so on. But for columns, we usually use these these 4. So either this one, the universal UC stands for universal column. H beam can sometimes be called I beam also, so be aware. And then this one, CHS, SHS, RHS. This one is circular hollow section, square hollow section, and rectangular hollow section. Hollow section. Yeah. So yeah, just to make you aware, there are like these sections. Okay. For columns is these four. And then yeah, let's go to the next concept. This one I think you're also pretty familiar. It's the major and minor axes. Okay. So I'm using the I beam as an example here. There's most sections have the strong and the weak axis. So the major we usually name it as YY. The weak one we name it as ZZ. So YY, if you see the diagram, YY is this line. Okay. So it means use your right thumb rule. So the thumb is the axis, and this is the direction of the moment. So for YY, the moment will go this way. Okay, so if you see the 3D, it will go something like this. So it's around the axis. Okay, same for ZZ. So ZZ means it goes this way. So this is ZZ. Okay. Why is YY stronger than ZZ? Is because the amount of what's it called, cross section, right? It's more spread out. So if you see YY, right? So YY is this line. If you see, most of the mass, right, is located away from the axis. So more mass away from axis. So means the IY is higher lah. Well, if you see ZZ, so this is ZZ. So this is the bending, right? If you see some of the mass are more mass is located in the axis lah. That's why it's weaker. So it's big. So IY is bigger than IZ usually. Yeah, this is just some concept lah. Why there's like strong and weak axis. Okay. Of course, the stronger one is stronger in bending and less susceptible to buckling, while the weak one is the opposite. Okay. Take note that not all cross sections have a major and minor axis. So, for example, CHS and SHS. So this is HSS. This is CHS. If you see the YY and ZZ, it's the same. Same for CHS is anywhere the same. So yeah, not all cross sections have weak and strong axis. This is just something to take note. Okay, so two concepts done. Now let's go to the third concept. So it's this one, beam to column load transfer. Okay, so just now I said, right, we have slab, loading from slab goes to beam. From beam goes to column. So ideally, so you have a beam like this, right? This is your support. Ideally, your column should be like this. So in the middle like this. Why? So let's say you have a reaction here, right? Let's say this is A, this is B. So this is AY, this will be BY. It will directly, what's it called? Directly transfer to the column, like straight to the column. So that's the ideal case. But in most cases, the beam is not located exactly at the center of the column. We call it eccentric. Okay? We call it eccentric. So if you see this image here, right? So let's say this is your beam. Okay? And then let's say this is point B. So let's say it's this point, that point B. Okay? Your reaction, right? It will be transferred around here. So if you notice, right, it's not at the middle of the column. Ideally, you want to transfer the load here. So beam, column, directly transfer. But in this case, the transfer is a bit off from the middle. Okay, so what happens is, let's say this is your reaction. Let's say this is BY. Okay, so the column will be subjected to BY as well. Okay, because the load transfer is the load is transferred basically from the reaction of the beam to the column. However, since this is not exactly at the middle, we have this called eccentricity. We call this E. Okay, so if you notice, there is a transfer of axial force, but at the same time, they also generate a bending moment due to the eccentricity. Okay, it's a bit off. So instead, so not only it transfers dy, it also causes a moment at the column. It also causes a moment. So the moment is just by multiplied by e. This is the force, this is the moment arm. So that's why we have the moment by times e. Okay. Tell me if I'm speaking too fast. This one, yeah, because I'm trying to get to the question also. Anyways, so if you see a column like this, right? So we have 4 beams. So let's say this is reaction 1 from the beam. Okay, I'll draw it like this. So this is the beam, this is reaction 1, reaction 2, reaction 3, and here is reaction 4. Okay. Okay, I'll draw 2 only because 4 a bit confusing. So this R1, this is R2. So this is E1, this is E2. Okay, and then there's R3 and R4. So the column, this column will receive axial force of R1 plus R2 plus R3 plus R4. That's the axial force. Okay, so besides axial force, since we have this eccentricity, right? Like this force is not exactly at the middle of the column. So we have a moment. So we have moment by this guy, this beam. So let's call it M1. So this M1. We also have here M3. So we have here M2. We have here M4. Okay, it's a bit not visible. M2, M4, this M3 and M1. Okay, so in this case, what's the total moment in the column, right? It's basically, it's not 0. It depends on the it depends on the moment. So let's say we have this column, right? This is the column. Yeah, this is the column. Yeah, this is the column just now. So in the end, we have a moment about this axis my, right, which is the resultant of m3 and m1. So it's basically m1 minus m3. Can you imagine, right? So you have the column, m1 goes here, m3 goes here. So you just take the resultant, that's my. At the same time, we have this direction, which is mz. So in this case, it's just m2 minus m4. Yeah, it's just, you can imagine it's like a seesaw. So this is your column, this is your 2 beams. Yeah, just balance out the moments. Okay, so minor and major done. Beam column load transfer done. So now we go to the this one. So wait, so somebody asked, so basically eccentricity of a column is the moment arm. Yes, correct, it's the moment arm. So it's basically how far the force is from the centroid of the column. Yeah. Okay, so now let's talk about the eccentricity just now. So the question is, how much is this eccentricity? Okay, usually it's given. Okay, sometimes it's given if we know the exact value. However, most of the time in design, we just assume. So the assumption is the eccentricity is 100 millimeters from the column face. Okay, column face, not the centroid of the column. Be careful. From the column face. Okay, not centroid. Okay. So okay, let's go back to this beam, right? So this beam just now, if we take the bird's eye view, right, the top view, it becomes like this. So what this means, right? 100 millimeters from column face. So this is the major axis. So it's, yeah, let's say it's this beam. Let's say it's this beam, is this one. Okay. So this is your load x here. So it's 100 meters from the column face. So the column face is this one, right? The one I'm highlighting, this one. this blue green line. So this is 100 millimeters. So if you're taking the moment from the centroid, right? So what's the moment arm? It's basically 100 plus h/2. So it's really just logic actually. Okay. So the same case for minor axis, again, it's 100 millimeters from the what's it called? Column face, yeah. So it's this line. So it's 100 millimeters from there. So from the centroid, it's this thing, which is TW/2 plus 100. So that's how the formula came to be. Okay, but this one only applies for IB. For CHS, RHS, SHS is a different thing. But the 100 millimeters from column face is a fixed constant. Okay. So I hope this one is clear. So the moment is caused by the eccentricity of the point load of the reaction force of the beam. Okay. So these concepts, I hope you are clear. Eccentricity. Okay. Next one is this one. It's the simple frame construction. So actually we're done with the column. Now we're talking about the whole structure. Okay. So simple frame construction basically means all joints are pinned. So let's say you have a beam going that way, then you have a column going that way, something like this one, let's say. This is 3D view, huh? Something like this. So these connections, so this, let's say, is the second level, something like this. Yeah, so these dots, right, are all joints, pins. Okay, so it cannot resist moment, I guess you can say. So this paragraph, so the moments induced to the columns are only nominal moments due to eccentricity. So what this means, right? I'll demonstrate it first. So let's say you have a beam like this. Okay, so this is a simple beam, so pin, or simple beam. If you see the bending moment, right, it's going to look like this. So this is M, this is X, something like this. So if you notice at this point and at this point, the moment is 0. So since your column is here, your column is something like this. It's here, right? Your column is here. So there's 0 moment transferred to the column. The column doesn't help the beam to resist the moment. The one resisting the moment by the load, right, is just the beam. So that's what it means by simply supported. So there's no moment from the BMD, but there is moment from the eccentricity. So these two are different. Huh? One is bending moment from the BMD, the bending moment diagram of the beam. One is from the eccentricity. So for simple construction, there's no moment transferred from the beam to the column, just from the eccentricity only. For rigid construction, so simple construction, right? The opposite is rigid. So for rigid construction, it's fixed joint like this. Let me draw. Okay. So it's a fixed joint. Your column will be somewhere here. Okay. So if you draw the bending moment diagram of this thing, it will look something like this. Something like this. Let me draw it better. So this is M, this is X. So if you notice, at the support, the bending moment is not 0. Okay, so we call this, let's say, MA or MA. This is A, this is B, let's say. Okay, so your column, right, will be supporting MA, will helping MA. Okay, so if you have a column here, if you have a column here, there will be a moment of MA plus the eccentricity. So, okay, how to explain it? So this is rigid. This is your fixed joint. So you will have something like AY, right? AY and MA. Okay, so the moment on the column is MA plus AY times eccentricity. So there's two components. One is from the transfer, so the beam, right, have this moment, it transferred to the column, so that's MA. And then secondly, your beam has a reaction AY. AY is not located exactly at the center, so we also have AY times E. So this one is because of the fixed joint. This one is because of the eccentricity. Okay, but don't worry, this one is only for rigid construction. For pin or simple construction, so I'll draw it again. So this is AY, right? This is DY. Okay, so if this is your column, so we have a moment here, right? Let's say a moment here. So the moment is eccentricity, so AY times E. But then look at this moment. The moment at the end is 0. So it's 0 plus AY times E. So there's two components. One is from the BMD, one is from the eccentricity. But in simple constructions, we only care about the eccentricity only. We don't care about the BMD because the BMD will always be 0 because it's spin, all pin. Okay. If you a bit confused, it's fine. This one won't come out, but this one I'm just saying that to give you some definition, to give some feeling on what is simple construction. Okay. Okay. So we are done with this simple frame construction. This one you just read yourself. Why do we use simple frame construction? It's because simpler to construct, easier to analyze, because if you have fixed joint, right, we have three unknowns: AY, AX, and MA. Simple construction, we just have AY, AX, so less unknowns. And then, yeah, allow gaps. This one is also simpler to construct. This one is, yeah, simplify the structure. So, yeah, this one is pretty straightforward. So far, anyone confused? This one is still concept, still concept. Yeah. If no one confused, then okay, we continue. Just one more page of concept. Don't worry. Okay, the last concept, one before last of concept, right? Is this one? Is the moment distribution. So if you see, right, this is your beam. This one is your beam. So we have beam N, beam E, beam W. Okay. If you notice, each beam is connected to two columns, upper one and lower one. Okay, so this is your beam. You have the upper column, you have the lower column. So let's say this beam south, right, south beam, S beam. Okay, so this will have a bending moment this way, right, which is P times E, or whatever you call it, like, is the reaction force times eccentricity. Okay, so this moment will be carried by the upper column and the lower column. So it's not one column resisting, it's two columns resisting. So you have a moment, it's resisted by two columns. It's the upper one and the lower one. So actually, right, it's divided. So you can divide how much the upper column takes the moment and how much the lower column. So let's say this is PE. Let's say the upper column has the resistance, or not resistance. The upper column, let's say, will take M1. The lower column will take M2. Let's say, okay, let me change ML and MU, upper and lower. So this eccentricity, right, the moment by eccentricity, P times E, is resisted by the upper and the lower. So upper plus lower. But we don't know how much is upper and lower, right? So it's actually by ratio of stiffness. Yeah, so actually just need to follow this. Okay, this is a diagram. So, okay, this blue line is your beam. This blue line is your beam. So you have a moment here, right, to the column. So if you notice, right, it's taken by the upper column, which is this one. So this is M upper. This one is M lower. Okay. So how you know MU and ML is using the stiffness ratio. So stiffness ratio is EI over L. So stiffness is EI over L. Okay. So E is elastic modulus or Young's modulus. I is your second moment of inertia, second area moment. This one is just length. Okay, so this is saying, so you take the ratio between the upper divided by lower stiffness, okay, or lower divided by upper, as long as the ratio is more than 1, okay, and then you check if the stiffness ratio is bigger than 1.5, you need to take account of the ratio of the stiffness. Okay, so you take the ratio. If you notice, this one is stiffness of the upper column divided by the total stiffness. So it's just simple ratio. However, if your stiffness ratio is less than 1.5, it is okay to assume that it is split half-half. So let's say this is PE, right? So PE, let's say if the ratio, right, stiffness ratio, so KU divided by KL is less than 1.5, right? We can just say the moment carried by the upper column is PE divided by 2, by the lower column is PE divided by 2. So half-half. But it's only if the stiffness ratio is less than 1.5. If it's more than 1.5, you need to take the ratio. Okay, that's all the concept actually. So let's review a bit. Major and minor axis. And then we have the eccentricity. Then we have the still eccentricity. It's just the value is 100 millimeters from the face. This one is simple frame construction. So basically saying if pin, right, the moment on the column is only from eccentricity. But if rigid, eccentricity and the BMD. So it's a combination of the two. And then lastly is upper and lower column. It helps to what's it called? Resist the moment. So both up and both lower column. Okay. Lastly, in columns, they are subjected to 3 things. One is buckling. Okay, buckling is okay. Let's say you have a ruler. I don't have a ruler right now. No need lah. If this is a ruler, right, then you put like some force, like compression, right? It will like bend. That's buckling. Okay. Okay. What should I use? Okay. So thanks. So this is your what's it called? This is your ruler. So if you press like this, right? This is your axial. So I just press down. It will tend to, yeah, it's like it's going to bend one way like this, right? Yeah. So it's buckling. It's biaxial compression. Be careful, biaxial compression only. So it's I'm only pushing down. I'm not bending. I'm just pushing down. So that's buckling. Second one is bending moment resistance. Now this one is bending. So bending moment, right? So just now is P times E. So I'm going to bend. So I'm legit going to bend this time. This is the bending resistance. So one is just buckling. It's just I'm pressing down. One is bending. I'm bending the thing. I'm twisting my arm. And lastly is LTB. LTB is also me bending, but it has a twisting, how to say, a twisting movement, I guess, like twisting like this. Yeah, so you need to check these 3 individually. So check for buckling, check for bending, check for LTB. Once it's done, you're not done yet. You need to do the combination check, which is this one. So 4 things, buckling by itself, bending by itself, LTB by itself, and combined check. So these 4. So if you remember, in beam, right, we have what? Shear, moment, LTB. This one we have 4. Yeah, it's axial, bending moment, LTB, and combined. Yeah, so that's all the concept you need to know actually. Okay, Ken. So we do the questions. Okay. Actually, this won't. Okay, this is just a spoiler. This won't come on quiz 2. like this thing. But I'm just telling you this so you know like the whole process. Because like in practice, this is what you see. I think this is in your tutorial also. So I'm just explaining this. And by the way, this question is taken from my first peer tutorial. So we don't need to calculate anymore. Okay, but okay, see how that. So I think I'll skip to this one. I'm going to just do one question only for this one. If we have time, we'll do more questions, but I'm going to do number 4 only. Okay. So what's the question is about? If you remember, right, the steps of design, you need to know the loading first. After you know the loading, then you can check. So what we're doing now is just finding the loading on the column. Okay. Sometimes in the question it's directly given, but in this one it's not. So I'm trying to let you practice like how to get the loading. So find the axial force and bending moment induced at the columns. So the question is simple. Basically, find the loading on the column. Okay, all columns are this size. You see 305, 305. So first things first, I'll use my book to find the the size first. I forgot to put inside the thing. Let's see. You see. You can practice to find the size also. So UC is 305, 305, 240. Okay, so here. So you have H is 325 point, sorry, 352.5. 352.5 millimeters. B is 318.4 millimeters. And then we have TW and TF. TW is 23, TF is 37.7. So if you notice, I'm doing this. Why? Because later, if you want to find the bending moment induced in the column, right? We need the eccentricity. That's why I'm writing this down first. I forgot to put something here in the question also. Assume simple construction. Assume simple construction. Because if it's rigid construction, right, it's not easy to get the moment because you need to consider the eccentricity and also the bending moment. So the beams are like rigid. So we're not going to touch that. That one is very complex. You need a program actually to do it. This one is all simply supported. Okay, so let's say we do column. Which one first? Let's do column A first, one. Yeah, let's do column A first. I'll label this M. Let's label this N, I guess. This is Q, this is R, this is S. Okay, so first things first, as I said in my first peer tutorial, right, always work backwards. So you start at the end point first. So what I mean, right, is let's say this is C. What I mean, right? So we have the column A. Column A is connected to which beams? We have 3 beams, right? We have beam AN, we have beam AC, and we have beam AR. Okay, let's start with beam AC. Beam AC. Okay, so for beam AC, where does beam AC gets its loading for? From, I mean, from. So this is AC. This is A. This is C. Okay. So again, you check for point load and check for UDL. So first things first, are there any point loads? There are none. Okay. Are there any UDL? It's the whole thing. Yes, correct. It's the whole thing. Thanks, Raymond. So it's the whole thing. Okay. So we have a UDL. So how much is the UDL? it's basically, oh, okay, the loading is this. So M is 1.35 times 4 plus 1.5 times 2. I think it's 8.8. Please check. I forgot. This is kilonewtons per meter squared. Let me get my calculator. This recording. Oh, it's recording. 8.4. It's not 8.8. 1.35. Yeah, it is 8.4. Yeah, sorry. It's 8.4. Okay, so we have the loading now. So beam AC will get a UDL of 8.4 multiplied by 1.5, which is this one. Okay, it's like the whole 1.5 will go to the beam. So 8.4 times 1.5, that's the UDL. So what's the reaction on A? I'm skipping a bit. What's the reaction on A? It's basically AY is equals to 8.4 times 1.5 divided by 2, because the beam AC is symmetric. So what's the value, I guess? 6.3. Okay, thanks. So that's beam AC. So let's check again. So beam AC done. Now let's go with beam AB. So this is beam AB. Okay, so beam AB is something like this. Beam AB. So first things first, you check if there's UDL or point load at beam AB. So beam AB is this thing. So this is beam AB. Are there any UDL? The answer is no. There's no UDL going to beam AB, but there's one point load, which is at point N. So there's like, so this is beam QN. There's point load at beam N. Okay. So point load at N. So this is A, this is B. Okay. So what's this point load? We check again. So the point load, comes from beam QN. Okay. Beam QN will get the load from here. Okay, so this is beam QN. So basically the load path will be like this. So beam QN will receive from the slab, something like this. And then it will split to half like that, like this. So it's like this. So beam QN, right? It's like this, then it goes this. Sorry, AY, no need to multiply by 6. Shoot, thanks. We forgot to multiply by 6 because this is 6 meters. Whoops. Okay, yeah, correct. Yeah, thanks, Jay. Oh my, okay. So times 6. So times 6 is 57.8, right? Yeah. Thanks, good eye, good eye. No wonder the numbers so low. Okay, so let's go to this one. So for point load at N, right, is okay. So the width of this thing is 3 meters. So it's 8.4 multiplied by 3 meters multiplied by 6 meters, because the length is this one, right? Then you divide by 2. Why divide by 2? Because beam QN, right? The load is split to Q and N. Okay, so it's like this. So here's the slab, goes to QN, half goes to Q, half goes to N. Yeah, so this. So that's what? 60 what? 75. Oh, 75.6. Thanks. So 75.6, right? Kilo newtons. So the reaction at A and B is what? I'll I'll just do A, right? So AY is 75.6 divided by 2, which is 37.8 kilonewtons. Same, right? Okay, so that's beam AB. For beam AC, to save time, sorry, for the other beam, right? There's one more beam, right? So the last beam is this one. It's beam RA. So beam RA. So beam RA is something like this. I'll draw it sideways like this one. Just this is top view, top view. This. Okay, never mind. I'll just draw it this way, just to avoid confusion. So this is A, this is R. Then so we have 1 point load, right, at M. We also have half of this, right? So we have something like this, and we have 1 point load at M. Okay. For this one, I don't think I'm going to do just to save time. Okay. I think the wait, let me count very quick, because I made this number very nice. So it's supposed to be 75.6. I think it's 2 times 3, 37.8. Okay, this one you try to confirm, but it's supposed to be 37.8 times 2. What's that? Oh yeah, 75.6. This is one. I made the what's that, the slab quite symmetrical. That's why I can think very quickly. This one you confirm, This one please confirm. This one asterisk one. Please confirm, because this one I just want to save time. Okay. I'm just going to do the IZZ. Okay. Oh, the IZZ is just nice actually. Shoot. Okay. So if you notice, right, this is beam A. Sorry, column A, column A. So if you notice, its shape is like this, right? So this is beam A. So one is connected by beam AC. So this AC. This is AB, right? Something like this. And there's one more which is going up, which is AR. I'm going to make this smaller. This AR, AB is C. So just now, right, we know that the reaction at AC, right? The reaction at A is what? 37.8. So AC is this beam. The reaction as 37.8. Here, beam AB, the reaction at A is 37.8. Okay. And then the eccentricity is actually the same. So in this case, so MEDZ, right? In this case, it's 0 because it balances out. So it's like a seesaw. Okay. If one of them, right, the AY is different, just need to minus the moment. Easy, right? It's like seesaw one. Okay. So for MEDY, so we have a force here, right? It's by the beam AR. So this one, right, 75.6. Not confirmed, but let's use this value for now. So it's just 75.6 multiplied by the moment arm. Moment arm is this one. So it's 100 millimeters, I mean, plus h divided by 2, right? Yeah, so h divided by 2. So h is what? 352.5. So 352.5 divided by 2. This is kilonewton, this is millimeters. So it should be in newtons. So I'll just multiply this by -3. So it becomes, let me check.
you get 20.9, is it?
Yeah.
Kilonewtons meter. So you have MEdy equals this, MEdz equals this. So I hope you get the point here. So from the, so this is just like quiz one. So you have the slab, you put it to the beam. But this one we have one more step further, I guess. So from the beam, right, we find the reactions. Then these reactions is going to be the columns load. Actually, we forgot one thing. It's a axial force. Axial force. This is just the moment, right? So what's the axial force on the column? Basically, just add everything up. So NED on the column. So NED is the axial force. It's just add everything up. So 37.8 plus 37.8 plus 75.6. So that should be, is it 151.2? Should be like, yeah, okay, nice. Okay, quick math. Okay, so easy, right? So from the now you know how to give from the slab to the column. Okay. So before we take a break, just one more thing. This one I don't include it in the. I forgot to include it here, but I think I included inside the cheat sheet. Let me check. Did I? SAM for CB3012. Sure. Okay. Yeah, this is my full version of the cheat sheet. Where is it? Where is it? Ah, here. Okay. I put it inside this box already. Yes, this. Yeah, this thing. So for axial force, right, you consider the current level and the level above. Okay, logically, right, if you have a column, right, of course it will need to withstand the whole floors up, like upstairs. Lah. So you have 7 stairs, right? The lowest column will resist 7 levels. Okay. But for a moment, we only consider the current level. Okay, we don't care about the upper and lower level for a moment. Okay, so do I have a picture? No, I don't have a picture. Oh no. Okay, let's say something like this. It's a very low quality diagram, but I guess it works. Okay, so let's say this middle portion, right, is your column. So this is AB. So that's your column, right? So I'll make this simpler. But I say this is your beam, level 1, level 2, level 3. Okay, it's a very okay. It's a okay. This is like first story, second story. Sorry, this third story, third story, second story, first story. Okay, so how to explain it? Let's say this is 30 kilonewtons, 30, 30, and we are interested in. Okay, this is B. This is A, B, C, D, E. Okay, there. So if you okay, let's say we are interested in this column AB. So this column AB, right? So NED, so the axial force on AB is 30 multiplied by 3. Okay, this is a very generalized example, but I'm just trying to give you what I mean. Okay, so you multiply by the number of stories. But for the MYED, let's say the MED on AB is just 30 times E. Okay, it's not 30 times 3 times E. This is wrong. Huh? For a moment, we only consider one story only. We don't consider the story above. Okay, so
let's take a 5 minutes break, 5 to 10 minutes. So we go back at 20. We go back at around 8:15 lah, 8:15. Let's go back at 8:15.
Okay.
Oh, thanks. Somebody is asking, sorry, why is Z 0 again? Okay. True. So it's because the left and right value is symmetrical, so they cancel each other. So oh, sorry. Okay, this one might be confusing. Okay, remember we have two axes. We have two axes. One is the strong axis. So this is YY. So YY will turn this way, and we have the weaker axis, which is Z. So ZZ is turning this way. ZZ is this way. Okay. So for ZZ, the one that is contributing to ZZ, right, is AC and AB. Okay, AC and AB. Okay. So the moment MEDZ, right, is actually 37.8 multiplied by this eccentricity. So what's this? I'll just write it as E lah, just for simplicity. Then you have another thing like here. So we minus it by 37 point like this. So that's why it's 0. Like the left and right cancel each other. While in YY, so YY spins which way? YY spins, spins this way. Okay, like this is YY, so it spins this way. So it's contributed by AR, beam AR. So beam AR will push that way, right? That's why it's 75.6, which is this value, multiplied by the moment arm, which is 100 plus this thing. Yeah. So yes, just like that. I hope that's clear. Yeah, so 20.9 is the y-axis moment, correct? It's the y moment. Yep. So I'll give you which picture? I guess this picture. So you can like imagine lah. So yeah, let's go. Let's continue at 8:15.
Okay, I guess let's continue. Yeah, somebody asked me to scroll here. So yeah, but this one is a very simplified diagram. You can actually see the better one in the question itself. But I'm just emphasizing that for axial force, you take the upper stories. For bending moment, you only take the same story. And then I guess before we continue the question, I think I can also add one more example. I think let's go. Okay, so let's say for something like this, then you have this, you have this, and like this, 50 kilonewtons, 30 kilonewtons. Then let's say this one is, let's say this E and this is E, like let's say. So in this case, right? So my, medy is 0. Why? Because there's no beam in the y direction. Okay. But medz is, so medz is again, is this one, right? This is dz. So it's basically just 50 times e, so the moment that way, correct, minus 30 times e, which is the moment that way. So it's 20 e kilonewtons meter. Yeah, this is just an example. So we have like two beams going like this. Yeah. Yeah, just in case they give you like four of those columns. What's it called? Four of those beams. Yeah, then you just cancel. Okay, so I guess we can go to the question. So this is actually from the, is it 2 years ago? Yeah, I think it's two years ago. My year was the same. It's just they changed the, so this one is, you see, right? It's a square value section. I think my year was a column, like it's not UC, universal column. So what's it called? They never really changed, but yeah, but it's better if you understand the whole concept, like this whole concept, like the one I explained just now from the very beginning. Okay, so let's just see the question. So the column is made of this square hollow section, grade 275, class 1, no need to classify. So they give already class 1. Then determine the compressive resistance. And then column buckling, effective line factor is 1.0. 1.0, it means pin. So if it's pin, the buckling is like this. So it's just 1. But let's say if it's pin fixed, sorry, if it's free and fixed, right, it's going to be like this. So it's 2.0. This one is buckling. I'll show you in my cheat sheet. I think it's this. Okay, so you're given the section, you're given the loading. You just need to find the maximum number of stories. So in this case, right, usually we are given the loading. From the loading, you choose the section. This one is a bit a reverse. This is the reverse the question a bit. Now you are given the section. Find the resistance, and then from that resistance, right, you need to calculate what's the maximum loading. Okay, so they reverse the question a bit. So this is the specification. Okay, so we are interested in column X, which is the lowest column, the base column, I guess you can say. So we need to find the maximum story. We are given the cross section like this. Then what else? I think that's it, right? So how to start? Wait, give me a second. First, you need to find the compressive resistance. Like I know how to do it. I just like how to like present it in a good way. Okay, let's find the resistance first. Let's find the resistance first. Okay. Yeah, resistance first lah. So for resistance, it's your okay. So this is the page that you should have, right? So remember, for column, we need to test three things. It's the buckling resistance, axial buckling, moment, and LTB. Okay, but in this question, they only ask about the compressive resistance, which is the axial buckling. Yeah. So yeah, compressive resistance means axial. So let's do the buckling first. Okay, let's do the buckling first. Let's do the axial buckling. So for axial buckling, in my cheat sheet, it's called this one, compression members, because buckling can only happen with compression. Okay. So actually, right, there are two types of resistance. One is the cross-sectional resistance. It's basically saying that given this axial, right, that let's say there are no buckling, what's the force for it to crush? So the first part of this sheet, right, is crushing. So you give some axial force, it will crush. Then if you see, right, the below one, right, is buckling resistance. Then this one is called the buckling. I guess for this one I'll do both. That's why not. Okay, so let me change compression member or compression check. Compression check. So let's do the cross-sectional, yeah, this one. Resistance. So it's quite straightforward. You need to find the NCRD. So NCRD in this case is what? It's just A times F1 divided by gamma M0. So the area is, this one is what? 250, 250, 16, right? 250, 250, 16. So it's 147. Yeah, I'm using the, what's it called? The table. Yeah. So it's 147. FY just now is what? 275, right? So 275 divided by 1.0, then multiplied by 10 negative 3. So that's 147, 275. It's 40.4 kilonewtons. Simple. So that's the cross-sectional resistance. We're done. Yeah. So by right, you need to check with the force, the effect, ED, NED. But in this case, since we are interested only in the resistance, we don't need to check for now. So that's the cross-sectional resistance. But then we need to check the buckling also. So buckling resistance. Actually, the buckling one is the more important one actually, because most columns they buckle first before they crush. Okay, so let's do the buckling resistance. So in this case, it's just follow the steps. So first, determine the effective length. So find LCR. So LCR is this one. You need to check, is it fix? Is it pin? Is it pin fix? You multiply the length by this factor, which is 0.85 times 0.7. But in this case, right, since it's all pin, you just multiply by 1. So it's just the same as the length. Right? So in this case, just 1.0 times length. 1.0 times the length in this case, right, is 4.8. Why is 4.8? Because we're checking this column. It's that simple. Okay, we're not checking the column above it, we're checking the lowest column, because the lowest column is the most critical one. Okay, because it carries the most weight. So it's 4.8 meters. Okay, let's go to step 2. Step 2, calculate lambda L or NCR. In this case, I usually do lambda L because it's easier to use. So in this case, I just use 933.9 multiplied by epsilon. So if you remember, epsilon is square root of, I forgot it. Did I put it here? No. Oh my. It's here. Yeah, 235 divided by Fy, right? Yeah. 235 Fy. Okay, so that's 86.8. I hope you all get the same number. Actually, I should put it up here as well. 0.92. Yeah, okay. Best practice is always list out the properties of the cross section. I'm a bit too lazy today. So. So yeah. Let's go to this one. So next step is to calculate this thing, which is okay. So class 1, 2, and 3. We are set. It's class 1. So it's this one. LCR divided by I. So it's LCR divided by I multiplied by 1 divided by lambda L. So LCR just now is 4.8. What's I? So I, you see the cross section table. I is the radius of gyration. This one, radius of gyration. What is this thing? Big I is second one. Yeah, this is small I. Okay, be careful. This is small I, not big I. So it's 9.5. 9.5 multiplied by 1 divided by lambda L. So that's 86.8. So yeah, let's just count. 0.006. Yeah, why is it very small? Something wrong with it. Huh? 4.8 meters. Oh yeah, correct. It's the units. Oops. That's why the one is very small. I is millimeters, right? That's one. Yeah, SCM. I is cm. Oh yeah, that's why. Nice, good eye. You need to use the correction. Okay. Make it SI, guys. So this one is 10^-2, and this is just 4.8. Okay. Lambda doesn't have a unit because this is just now is the same unit, so the unit cancels. So let's count. It's 0.582. Okay, so if you notice, no need to check buckling resistance if it's less than 0.2, but this one is more than 0.2. So check for buckling. Check for buckling. Okay, let's go next. Select the appropriate buckling curve based on H, V, and T. See next page. So this next page. So we have the, just now is the what? Is the square hollow section. So the square hollow section is this one. So if you see hot finish, any is curve A. So hot finish, any, this one A. This one is because we are interested in this one, S275. So buckling curve A. So buckling curve A. So if you notice, right, for I beam, we need to find the TF. then you compare with 40, then you get the buckling curve. And the buckling curve for YY and ZZ is different. So practice, guys. So I think the tutorial have the IB, right? So I guess you can refer from them. So for this case, it's just curve hallucination. So it's just buckling curve A. Okay. So follow section, spiral section. Okay. So buckling curve A. So let's go back. So choose alpha based on buckling curve. So alpha is just 0.21. Is this one? Is this one? It's legit just follow the steps. Okay. So if you notice, right, this is quite similar to LTB. It's calculate some stuff, find the buckling curve, find alpha, then just continue. So it's actually not that hard. It's just getting the loading and just be careful when doing stuff. So this one is just 0.5 multiplied by 1 plus alpha is 0.21. That thing is what? That thing is 0.582 minus 0.2 plus 0.582 squared. So help me plug this in. 0.5, 1 plus 1, 0.582, 0.82, 0.709. Okay, so next step is calculate the chi. So chi is 1 divided by 0.709 plus square root of minus 0.582. So what's that? 1 divided by 0.709 square 0.709 square. Square. So it's 0.898. I hope you all get the same numbers because I'm often wrong. So lastly is the buckling resistance NBRD. So NBRD is chi multiplied by A times Fy divided by gamma M1. So that's what? 0.898. That's area. Area just now is what? Area is 147. So 275. Gamma M1 is 1. So this one I multiply by 10 negative 3 to make it kilonewton meters. So 0.898 times 147, 275. So it's 36.3 kilonewtons actually. Why is it very low actually? Something wrong here. Give me a second, let me check. Cm squared. Oh, okay. Oh wow, okay. Thanks. Be careful, Always check the units. Okay, no wonder. Okay. You always need to check the units. It makes sense. That's why. Okay, that's how you check. If the number is like lower than you think, right, is probably wrong. Okay, so wow man, is what? 147. Wow, if I retake this, right, I'll probably get C. Oh shoot. GG. Cm squared. So cm squared to millimeter squared is 10.4700 mm squared. Ah, okay. I will take that C. What the heck? Okay. Okay. Okay, so 14700 times 275. Ah, this makes more sense. So 404.3. So that's for the cross-sectional resistance. Because logically, right, if you see, right, this one is 150 already. If it's like only like one story, then cannot do it. Okay. Okay, let's calculate this one. So it's 0.89. 363. Okay, so we have the buckling resistance, which is 363. So first part of the question is done. Why is 360 so low though? I'm also sus. Oh. Hmm. Wait, let me think. Honestly, I used to do this, but I forgot. It's like deleting. Oh my! You press wrong calculator, really? Wow, always, yeah. Every paid tutorial I made like some mistake. Aiyo, give me a second. This is 250 by 250. Okay, this is why it's a good practice to always write, like copy out the values first. Don't jump like this. Huh. I remember the answer is like 7 stories. This one is very low. Something wrong. Oh. Uh, so it's 147 cm squared. So cm squared to millimeter squared is 10 squared. So add two zeros. Fy is this thing. Epsilon is that thing. 9.5 centimeters. Hmm? I haven't found the issue, guys. Wait. This is not good. Fy is Newton per millimeter squared. Hmm. Yeah, the unit is Newton per millimeter squared. It's Newton. So if this is Newton per millimeter squared, this is millimeter squared. Cancel, it's Newtons. Newtons times this kilonewtons. Should be correct, yeah? Oh, guys, okay. I see wrong the decimal point. Oh, it's 404.2.5. Oh my, okay. Oh, it's my writing is correct. It's just I see wrong. Oh, okay. It's okay. So this is 3630.2. This makes more sense. And that guys is how you cross check. Oh well, okay, can. So now we have the buckling and cross-sectional resistance. Okay, what is the maximum number of stories? So we are asking about the compressive resistance. Actually, like for this question, how to say? So if you remember, right, there are like 4 things to check. What is it? So in by right, there are 4 things: axial, bending moment, LTB, and combined check. But actually, right, usually, I'm saying usually, usually for column, the most critical one is the buckling. Okay, it's always the buckling which is the most critical usually. So that's why in this case, right, assuming buckling is the most critical case. Okay, it should be axial buckling. Axial buckling. Okay, so we have our resistance, which is this. Okay, so the column, our column, right, can only resist this much force. Okay. Actually, okay, give me a second. Let me gather my thoughts. Okay, let's do. Okay, axial buckling done. Let's do moment. Let's do moment. So for moment resistance, so just now is what compression check. So now moment check. So moment resistance check. This is actually less critical, but I'll just check. So for moment resistance check, we just follow this one. This is your classic. This one. It's quite simple. So for this one, the MCRD, because it's class 1, right? It's just WPL Fy divided by gamma M0. So WF, in this case, WPL is what? WPL is, this is, remember, the unit is cm cube. 1280, 1280. So 1280, your unit is cm cube. Let's make it SI. So it's times 10 to the negative 6. And y is 275. Let's make it SI also. So it's this one. 10 to the 6th. So 10 to the 6th divided by gamma MO, which is 1. And then I want to make this kilonewton. So that's why I make it -3. Okay. So that's 1280 times 275 divided by 1000. So it's 3, 5, and 2. 3, 5, 2. Okay, done, right? So remember 3 things. Axial, we're done with axial. Moment, we're done with moment. Lastly is LTB. However, here's the catch. For LTB, this one, simple construction, right? This one, this clause like here, the very bottom. Ayo. So here, for CHS, SHS, or RHS, the LTB resistance for simple columns. So LTB resistance is equals to the moment resistance. Okay, it's this one. Okay, so why is that so? This I kind of forget why also, but the easy explanation I can say, right? LTB is, it's like this. LTB only happens at the major axis. Remember, LTB only happens at major axis. LTB only happen at major axis. The Y itself, right? You need to research because I don't know it. But it's like the tendency for it to twist like this, right? Is just on the major axis. So logically, since it's only happening on major axis, if your section, right, doesn't have major or minor, no LTB. So that's how it works. So that's why CHS and SHS, LTB, right, don't need to check. It's the same as the moment for hollow sections only. I don't know why RHS is here, but I just copy the lecture notes. If you want to make sure, right, ask the prof, please. Yeah, ask properly. This one I forgot why, but LTB only happen at major axis. So okay, this one I'll just grab. I'll just say. So for LTB, so LTB resistance. for HSS, MBRD. So MBRD stands for LTB. I think B is for bend. Is it B for bending? I'm not sure because C is for moment resistance. So I don't know about the letters, but just say that MBRD is equals to MCRD. So this one is from moment, which is 352. Done. So we have the three resistances. We have the axial resistance, we have the moment resistance, we have the LTB resistance. So we have three now. So now the second question is what? Second question is find the maximum number of stories. So now we just need to see the actions. So here we have 150, we have 150, 120, and 170 for one story. So this is for one story only. Okay. So here, right? So for one story or one level, up to you what you want to call it. Let's calculate the axial force because the axial is easier, right? So for NED, it's basically just add everything up. So it's 150 plus 150 plus 170, 120, 580, 590, right? So that's NED for one story only. One story, yeah. I guess I'll put a one there, just to indicate. So one story. Then for moment, we have two axes, YY and ZZ. So MYY, let's start with YY first. Actually, we don't have YY and ZZ. So we just take the maximum one. Okay. So okay, let's indicate X and Y now. So here. So for MYY, YY first or XX first? XX first, MX. MEDX is so X is where? X is this one. So the moment goes this way. Okay. So it's affected by 150 and 120. So it's basically 150 minus 120 because we're taking the resultant. And we need to find the eccentricity as well. So eccentricity. Okay. So the eccentricity is, remember, it's 100 millimeters from the column face. So this one is 100 millimeters. And this one is basically just h over 2. Correct? So it's just 100 plus h over 2. So that's 100 plus what's h? 250. Okay. So 250 divided by 2. So that's 225 millimeters. Okay. So that's eccentricity. Now what? So you find the moment. Let's go. So one. Okay, I'll make it the full form. So it's 150 multiplied by 225. So that's the moment this way. Now you will find the moment the other way, which is different. So with minus 120 times 225. So that's 6750, yes. Kilonewton meters. MEDY is since this is a square hollow section, right? The eccentricity everywhere is the same. So in this case, it's just 170 times 225 minus 150 times 225, which is 4,500. Okay. Okay, so done. So so which one do you use? Is this one? Okay, so this is for one story. So This one is raw. This one is raw. So this one is raw loading. Okay, so this is for one story. Yeah, remember this is for one story. I'll add one more page. So for column X, okay, so for column X, right? Remember, column X is the bottommost. So NED on column X, since the loading on each level is the same, right? Like this one is for all levels. So it's basically saying it's just 590 multiplied by the number of stories above X. You get what this means, right? So 590 multiplied by, let's say, N line. So N is the number of stories above column X, correct? So 590 multiplied by N. And then for the moment, remember, for the moment, right? Actually, what's the moment here? The moment here is 0. Because it's simple construction, all pin. Okay? How about the moment here? It's not 0. The moment here, remember, we have 6750 and 4500. But remember, we need to split up and down. Not divide by 2. Depends on the stiffness. Be careful, depends on the stiffness. Close enough, close enough. So, do this again. Yeah, so if you notice, right, it's not following this cheat sheet. Why? Because this question, they flip the thing around. So, yeah, for you to remember. So, you have the stiffness here, right? This one. So, so stiffness, right? So stiffness ratio. So stiffness ratio is EI divided by L. But in this case, right, since this whole column, the whole story, right, they use the same section, the E and the I is all the same. So you can cross out later. Yeah, so EI divided by, so the lower column is what? 4.8, right? Divided by 4.8 divided by EI divided by 3.5. So what's the value? So this one you cross out, right? 1.37. Wait lah. Wait. 1 divided by 4.8 divided by 1 divided by 3.5. Why is 0.27? Yeah, it's 0.72. So if you notice, right, I actually purposely do this. Legit, I purposely do this. Ratio must be bigger than 1. So if the ratio is less than 1, flip the thing. Flip the thing. So it's supposed to be EI divided by 3.5 divided by EI divided by 4.8. So this one is what? 1.37. Okay, so I'll put a note here. So less than 1. So ratio less than 1. It means denominator and numerator is flip lah. Flip denominator and numerator. Okay, so 1.37. So 1.37 is less than 1.5. So split half. So split half. So basically it's saying this column up here, right? I'll just draw. So this is your beam. This is the upper column. This is the lower column. So this is column X. So just now we have 6750, right? So 6750, half of it will be carried by the upper column, half of it will be carried by the lower column. Okay, so this is 0.5 times M is 0.5 times M. Okay, so I'll just write this down. So MYED and MZED for column X. So for column X, for column X, MYED is just 0.5 times something. 6750, 6750, and 4500. Actually, I'll make this X and Y just to keep the consistent. 6750 and 4500. Okay. So what's half of it? 3375. Then half of 4500 is 2250. Okay. So this one is kilonewton meter. Kilonewton meter. Okay, so how to find the number of stories? Okay. This is already the end actually. So looks like something is wrong again. Is it the number of unit? 1280 times 274. No way. Sus, yeah. Wait, the number is very sus. Battery check 24%. Yes, thank you. WPLCM cube is 10 negative 6. 10 negative 6 to 70. I don't like this. Why is it like this? 30 kilometers. Give me a second, let me think. Okay, I'm not sure with the moment values here. It seems, yeah, it seems very big compared to 352. So basically it fails in one story, which doesn't make sense. So I'll go check later. But usually, right? Usually it's like this. So moment BRD is bigger than MED X. So this one is LTBN moment pass. Okay. So this is the first step that you need to do. If this doesn't pass, it means it doesn't support, it can't even support one story because it fails by moment. Okay. But once the moment is passed, then you can check how many stories you can handle. So how do you check? So just now we know that NBRD, right, is 3630, right? So NBRD is 3630.2 kilonewtons, right? And then remember that the force on column X, right, is 590 times N kilonewtons. So 590 times N. So this one should be bigger than 590 times N. So N must be less than what? So 6.15, right? So it'll be less than 6.15. Therefore, n is 6 stories. Remember, 6 stories above x. Okay, 6 stories above x. Above column x. So if column x is like this, something like this, right? So this column x. So if you see the picture just now, this is column x. It can support 6 stories. But then remember this one they say is like first stories counts from the one below. So including the ground level. So it's 7 stories, including ground level. Yeah, so done. We're done. Okay. This one is compared to the first pre-sorting is a bit everywhere. It's because the question is flipped. So it doesn't follow the normal structure. But I hope this helps. So I'm not sure with the moment. I don't know why the moment is off. Where's the moment off? Each is 250, right? 225, this one correct, right? 30 times 30 times 10 to the third times 225 times 10 to the 6750 divided by 5. Sus. This one is very sus. I don't know why this one. Let me check again, huh? Once more, WPL, WPL. I can't take it yet. WPL is 1280. 1280. 1280. Then FY is 275, right? Divided by 1. Okay, this one I think I'll check again lah. Yeah, but for now it's like this. So you find the number of stories from the buckling actually. Yeah, because moment they only consider one level, while the axial, right, they consider the whole like top levels. That's why you use the buckling one as a reference. Yeah. So that's all actually. That's all I had for today actually. So if you have any questions, right, including the one from the tutorial, I think the one in tutorial, right, they follow the flow more because they give you the what's it called? They give you the loading and you need to find the you just need to check lah basically. Yeah. So this one is the question a bit reverse. Yeah, that's all actually. Any questions? Let me scroll up. Okay, let me see the chat first. MEDX is 6750. 225. 30 kilonewtons times 225, right? Yes, 30 kilos times 225 is 6750, right? Yeah, I don't know. I don't know what I don't know what's wrong with this. Because if the moment fails, right, it cannot even support one story. So I'll check again. I'll check again. I'll check again. I'm very confused now. CM cube first cube is 6. Okay, never mind. Never mind. If the moment fails, then just say it cannot even support like one story. But if it pass, right, it should pass like, the whole thing. Yeah. Yeah. So any questions? Any questions? I only have 22% of battery left. Yeah. Yes, and it's times 10 to the power of -3. Eh? Oh, oh my gosh, thanks, Usma Chung Chung. But okay, thanks, man. Okay. Okay, shoot, I found a mistake. Ayo, this is kilonewtons, this is millimeters. So this thing is Newton meters. Okay, thanks. So this one, you need to multiply by 10 -3, so it's 6.75. This one is 4.5. Okay, makes more sense. Wow, units, yeah. Okay, done. So 6.75 and 4.5. So even that, right, you need to divide by half. So it's very small. So 6.75, 4.5, 3.38, 2.25. So this one, MBRD is 352. Okay. So MEDX just now is 6.75, right? 6.75, which is way lower. Yes, yeah. Ayo. Units. Okay, done. Wow, good job, guys. Good job. Okay. So that's all. Yeah, really that's all. So this is resistance, right? So this gets checks. Actually, you can do extra by yeah. This is n equals to 6, right? N equals to 6 stories above column X. Yeah, this one you can actually do the combine check also. But combine check is just extra actually. So combine check is combine check. This is just in case of. So let me see. Okay, so for combine check, for simple construction is this. So it's NED divided by that thing. So NED just now is what? It's 590 times N. So 590 times 6, right? Divided by just now is this one, 3630 plus 1.0. MYED is what? MYED is 6.75, which is very low. 6.75 divided by 352 plus 1.5. Moment about the z-axis, right? Moment about the z-axis just now is 2.25. And 2.25 and 3.38, right? Yeah, 2.25, 3.38. 3.38, 2.25, 3.38, 2.25. This one is 350 equals to so this one is equals to what? Let me check. This is 0.9. Wow, 0.994, yeah. It's 0.99. This is the combined check, 0.994. Still less than 1. So okay. Yeah. This one is okay. So this one is just check. So let's because this calculation, right, the number of stories is based on the buckling. So you get what I mean? So from buckling resistance and buckling action, right? Sorry, action, right? You want to find the number of stories. Then to double check again, right? You put it back again to the check, which is the combined check. So if the combined check pass, right, it's definitely okay. Yeah. So yeah, that's all. I will reorganize this because honestly, doing it while talking is yeah, fair lah. Okay, I'll send it. Yeah, so that's all. Hope you all understand that, especially the concept lah, because this is like after the concept is just application. Okay, that's all. Any questions? Any questions? Have you got just don't get not in.
So is that do the same thing as part one, right? So that we do the one check.
Yes, that's it. Really, it's just a different type of check, but the flow is the same. That's why. Yeah, the difference is just this one they ask number of students to same. Right. It's like honestly,
But the note transfer you need to do, right? What's the loading for?
if it's the same as last year. If it's the same as last year.
Let's follow this cheat sheet.
Who's Ben?
You want?
You want? Two red cards. Oh, GG. Somebody watches football.
Yeah, the guy.
Okay lah. So that's it, I guess. Any questions? Any questions from that side? Yeah, done, guys. Thanks for everyone who helped lah, because I common make mistakes. Ah. I can give you like just my structure, which is very
Like one picture, right?
yeah, but legit like most people like they add like examples and do stuff like I know.
Yours either, right? As in got face relationship with it.
You get it.
Okay, but finals is one.
Yeah, finals can.
Finals.
Yeah. Structure. Wow, shit, like wait. Is it the tower?
Yeah.
Oh no.
But the thing is, he changed one last part to the stiffness matrix.
Oh yeah, but
That's structure.
huh? Really?
From what
I thought it's the
yeah. So as in
oh
when closer to the date, can I just ask you?
yeah, okay. It's just fuck, do I need to rewind? I don't think so. Okay, guys, it's done, guys. Legit, if no questions, I can turn off this thing. Yeah. Oh, yeah, please fill in the feedback, by the way. Is this one? Ta-da!
Bye.
Yeah, bye-bye. Thanks for coming, man. Sorry, may I know when to use hot finish? It's always hot finish. In Singapore, the production is always hot finish. That's why we always use hot finish. Unless stated. Yeah, so the wait. Yeah, that's it. It's always hot finish. Unless stated. Then what else? Oh, just be careful when you check from the book, right? Yeah, sometimes people forget to check the hot finish. They see the cold finish one. So just be careful because the properties are different, especially the W. Yeah. Any more questions? Solid good question. I add to my notes. Yo. Wait, let me find the notes, I guess. That is me. Moment resistance. Compression resistance. Yes, I will upload. I will I will upload this to the what's it called, to the tele. But I think I need to. Okay, this one I leave now. Like the first few pages I leave, but the bottom pages I think I need to make it nicer first, as usual. Yeah. So if no questions, I'll close. Thank you guys. Stop recording.